Thanks a lot. Can you all hear me and see my screen? Okay.
Yes.
Yes,
Yeah.
looks excellent.
Yeah, thanks so much for the introduction. Thanks for the invitation, and thanks to the organizers for putting together this nice event and the program. I have to correct you. I did study philosophy, but I don't have a degree in it. I gave priority to my PhD work and stopped studying philosophy, although it was a lot of fun. Yeah, so I'm very happy to be here and talk about basically work in progress from our collaborations and my lab, and that is transferring inductive biases from brains to machines. And I prepared an introduction, but it seems that like Emma did such a great job, and she did my introduction already. I'll just basically will go through that very quickly now. It's again about deep learning. So we all know that deep learning has a great success recently, especially in computer vision. And what I show here is the same what Emma showed you, just in a little bit different graph. So you see the top one accuracy of different classification performances on ImageNet, and you can also see that like since 2012 there's been basically a large increase in the accuracy, and this is all to deep learning. And pretty much everything that is related to computer vision and the state of the art in computer vision is deep learning at the moment. So they're not only classifying images, as Gemma said already, but they basically locate things in a scene. They can segment images into like pixel-wise regions of what has been seen in the image. And Gemma also already mentioned other applications. However, they are great, and they sometimes perform better on a particular data set than humans, but they are also pretty brittle. And what I mean by that, I will just give a few examples in the upcoming slide. So maybe some of you have already heard about adversarial examples. If you haven't, I'll just quickly go over that again. So what is an adversarial example? So you can take state-of-the-art deep network, let's say that has a very low accuracy on ImageNet, and then you can try to find adversarial perturbations. And adversarial perturbation is basically a kind of targeted noise. So it's very low in amplitude, so humans usually cannot see it when you add it to the image. But when you add it to the image, what's shown here, so you have an original cat image, and you add this adversarial perturbation, and you find with one method or the other, and you add it to the image, then this will completely derail the classification performance of the deep networks. And before the network correctly classified this image as a cat, now it will classify the image as a moped. Although, like for us, it perceptually hasn't changed. And not only is this network wrong, it's also wrong with high confidence. It's just, I mean, the network could be unsure what is on the image, but it's actually very sure that this is a moped and not a cat. You can find these adversarial perturbations for all sorts of tasks. So this is another example here. You see basically very well working segmentation networks. On the left side, you see the original image and the original segmentation, and then you can add adversarial noise. Again, you cannot see it, but the network pretty much gets the entire scene wrong. And in particular, it lost all the pedestrians. And you can imagine that this is a problem, in particular, for instance, when you think about applications like self-driving cars and so on. Okay, then you might think, okay, well, like this is highly optimized noise for a particular deep network. So maybe, but like how would I ever be able to simulate this kind of adversarial noise in the real world? Unfortunately, it also works in the real world, and I will just show you like a little picture from the authors of that study here. So what you see is a perturbed image. Now you can actually see the noise a little bit, and you can see that there's a classifier running on that cell phone. And on the left-hand side is always the original image, and on the right-hand side is the perturbed image. And you can see that the classifier gets it right on the left side, so on the original image, but it gives a wrong answer on the right-hand side. So let's see this again. Okay, here there should be a washing machine or washer with 52%. And then now it's a doormat, sorry. Let's maybe like look at one more. If there's one more, yes. Oh yeah, well. Okay, I think I just interrupted here. You get the idea. So you can simulate adversarial noise also in the real world. So that, and what that tells us is that the neural networks are basically using different kinds of strategies to classify these images, and this is also something that we like just heard in the questions before. There's other, like these networks are also not robust to input perturbations. And this is basically has been studied by Robert Garros. Just have this zoom bar in my window, and it's hard to get rid of. Okay, it's been a study by Robert Garros. So what they did is they took an original image, and then they used like a selection of perturbations on these images. They converted it to black and white. They did low pass filtering, band pass filtering. They scrambled the second order spectrum, and so on and so forth. And then they ask a highly trained classifier what's on the image. And of course, if there's no perturbation, so that would be like a points on the left-hand side here, then the networks perform pretty well. So that all the blue curves are networks. And when you increase the distortion severity, so here it's shown for uniform noise, then the classification performance drops quite quickly. And you see that all the blue curves basically drop down to 20% classification performance on for a 0.2 noise width. However, if you do that with humans, then the humans can classify that image correctly for a wider range of noise levels. And the interesting thing is, it's not that the networks are generally confused by noise. They can actually, if you train them on this particular type of noise, then they can learn to deal with it, and then they're actually pretty good at classifying the images correctly, although there's noise on it. Just when you show them a new type of noise, then they are again vulnerable to this distortion and drop very quickly in classification performance. And that's not only true for this one uniform noise, it's basically true throughout the board of all the different kinds of perturbations. So the pattern that you should see here is that always the blue curves drop quicker than the red curves, blue curves being the networks, red curves being the humans. So now you could ask, so why is that the case? So it could be that maybe the brain is more powerful and has more computational resources and is just better at computing things in images. I will argue that this is likely not the case, first of all, because these networks are actually pretty powerful. They are, if you have enough neurons, they can basically fit anything you want. You can overfit them on a training set, and as Robert already showed, you can actually train them on this particular type of noise. So it's not a question of power. It's and what I will argue is that it's actually a question of what I call, what others also call an inductive bias. That means what are the implicit assumptions that are given by the architecture, by the type of training, and by the learned weights that will determine how you extrapolate. And let me just basically repeat this idea with a toy example, because that will become important later. So let's assume, like a very simple example, we have some data, we have inputs and outputs, so in a kind of a linear regression setting, and we have some training data here. And now we use a network, and that network happens, is trained, and it happens to be a linear network. So the only thing that this network can realize are lines, basically. It's an affine function. And of course, that's a strong inductive bias, right? Because if you assume that it's a line, then this will determine how you will extrapolate your data. Okay, so in this case, the network can fit the data pretty well. And now we can show it test data. And if the test data comes from the same type of data that the training data, then it will, of course, do a good job, and it will then predict the data decently well. However, now the interesting question is, what happens if the network needs to extrapolate? And we really don't know how the data will extend. So it could, for instance, extend like this. So now if we use our network trained on the original training data, it will extrapolate like this, because it made the assumption that the data should extend linearly over it, beyond its domain. And then you can see that this network will basically will start to make mistakes. However, if you had used a different network, so I mean, this is a cooked up example, so I know like how I want to extend the data. So if you use a network that has sigmoidal functions, for instance, it could be trained on the same training data here, but it could extend differently beyond the domain and now fit this, what I call transfer test data. So test data is a little bit different than the original training data. It would fit that one better. And it's only because this network made different prior assumptions about how to extrapolate in its weights, in its activation functions, and so on and so forth. So the difference in performance and extrapolation is largely determined by what kind of implicit assumption this network makes. If you do make if the inductive bias, so your implicit assumption is not good, then you will not make good predictions beyond your domain. If it's good, then you will extrapolate nicely. And in fact, there's even like mathematical theorems that show that if you don't make any assumptions about your data, then you can also not generalize, and that's called the no free lunch theorem. So that's why there's no free lunch here. Maybe also no bananas and cookies. I don't know the joke. All right, and again, this flexibility and a powerful network is not the goal. And I also want to demonstrate this with a simple example because I think it's important. So let's say it's a similar situation. We have some training data. So those are the blue points here. And we want to, we fit this with like, in this case, with a polynomial up to degree 6. And then we test it on the black points, which are not that different. And what I did here is basically I bootstrapped the points and I got a different polynomial each time. And you can see that these polynomials are actually quite powerful. So depending on what points I pick, if I fit a 6th order degree polynomial, then beyond the domain, the polynomials can basically do what they want, and they will and they can be almost arbitrarily off on this black data. However, if I restrict my class, so if I only take polynomials of order 0, so constant functions, and 3, then I will, like in this case, because it's the right choice, I will extrapolate better. But notice that this class of functions here, so these polynomials, could also be expressed by this class. So all of these guys are inside this class here. So this class is more powerful, but its powerfulness in a way also prevents it from extrapolating nicely because it can do too many things outside the domain. And this class here is more restricted, so it can do only certain things, and in this case, unfortunately, the right things outside its training domain. So I would say that the reason why the brain is better, that it is actually restricted in a way, that it makes assumptions, and that just happen to be good assumptions about our natural environment. And this is the reason why it's so much better on the tasks that we usually perform and that we are so good on. Okay, now we could take a step back and think, okay, how could we actually get some of this inductive bias that the brain has and put it into deep networks to make them better? And there are probably many ways to think about it, but one way to think about it is in terms of David Ma's 3 levels. So if you don't know what these 3 levels are, so he basically says that you can understand a computational system on 3 computational levels. One is the computational level. So those are basically the objective functions. So what is actually the task that the system wants to solve? And this very much relates to what GEORG just showed us in our talk before. So you can train a network on like scene segmentation, object classification, object detection, and so on and so forth. And this will be different computational tasks. And maybe just because basically our network, our brain is one network that solves all of these tasks together, like Timo actually also referred to in his question. Maybe if you do that, then we get a network that does a better job and is actually better at extrapolating beyond a single task, because these tasks somehow create some kind of synergy together. So this could be the computational level. Then there could be the representational level. So this, I would think of this as what are the features, the functions that are actually computed on the image. So one example for representation is if you think about numbers, you can represent numbers in Arabic numbers, what we are used to, and you can represent them in Roman numbers or in bit strings in a computer. And some of these representations are just easier to compute with than others. And so that shows that representation basically matters. And similarly in a network, once you fix your set of weights, even though you have the same architecture, you might get different representations. So different features that are computed from an image. So maybe the brain just has better representations. It has learned some good nonlinear functions that are just exceedingly good at doing visual tasks. And then the last thing would be the implementation level. So this is how it's actually built into a physical system. And our brain obviously uses neurons, it spikes. We have different brain areas. Maybe we have cortical layers. We have interneurons. We have pyramidal neurons. All these things, maybe they matter. And probably all of those matter. But what we are focusing on at the moment, and I think there's many others, is the representational level. Because if you can imagine, or basically we already seen this in the talk before, that if you have the same network, you can train it on different tasks and you will basically get a different representation from this network. So even, and what that tells us is that the architecture of the network itself might not be that restricting. It will be restricting in some way if you think about the linear network versus this sigmoidal network, but maybe it doesn't put a very strong constraint on the function class itself. And in the end, it will probably, to find a network that performs as good as the brain, you will probably need something that takes into account many levels. And this is what I tried to show with this plot down here. So if you think about all possible functions that could be implemented on images, and then you put these different tasks on it. So basically, we want to look at all networks that can solve task 1, task 2, and task 3. You would be in this intersection here. Then maybe if you want to have like biologically plausible networks, you would take another intersection here until you basically the intersection becomes very small and you single out a network that hopefully does as good of a job at visual tasks than the brain. And we basically know that this intersection cannot be empty because we know that the brain exists. So this is an example of a network that can do all these things. So it's obviously biologically plausible, it can solve all the tasks, and it has a certain representation. Okay, so this was basically the conceptual background and like our way to think about this problem. And now we try to put this into practice. And of course, this is a complicated, this is a difficult task. So this is basically our first step into this direction. And that is neural code training on Monkey V1. And that's a collaboration with Andreas Tolias from Baylor College of Medicine, whose lab recorded the data. And the person who did all the computational work is mainly Shad Safarani, a master student in the lab, and 2 PhD students are Nix and Konstantin Mieleke. And if you want to read about this work, you can go to arXiv or to our lab webpage. There's a link there. We just uploaded it a few days ago, and you will also find, we also uploaded the code, but I'm not sure whether the link is there already. So if you don't find it, maybe go back in a few days and then it will be there. Okay, so what did we do there? We basically took this the idea of that representations are important series and just try to get a network that has a representation that allows it to solve a particular task, in this case, image classification, but also that has a representation that is similar to the brain in some sense. And we try to enforce this by also predicting neural activity from this network at the same time. So it's a multitask learning problem. So this one network needs to classify images, but it also needs to predict neural activity. And we call this idea the neural code training hypothesis. And the hypothesis is that it helps the network to extrapolate a bit better by making it a bit more brain-like. Can we expect this to work? Yes. There's a few previous works, some of which we have been involved already. So in a similar work before, we actually did something that goes more, at least the methods that we used in the direction what Gemma talked about is we used a representational similarity and tried to match that between the brain and a brain of a mouse in this case, and between a classification network. And there we observed that we could get improved robustness against distortions from Gaussian noise and also adversarial examples. So this is very closely related, and it gives us hope that this could actually work. There's then, like shortly after that, it was another work by Federer et al., who basically used the same idea only on monkey data, and showed that you get some kind of improved robustness to label noise and some other advantages by representation matching between brain data and networks. And there is work by a group around Di Carlo, in this case D'Apello et al. In 2020, who showed that if you make a network more robust against distortions, then you can also predict neural activity better. So in a way, it's the other way around. They make it more robust and predict neural activity better. We want to predict neural activity and want to make it more robust. Okay. All right, so this is the network. This is how we actually did it. So we used VGG19. We determined the best layer to predict monkey, so macaque V1 data. And then we put a readout head on this layer with a special readout that we published for mouse neurons before, and that we used to predict the spike count per neuron when looking at particular natural images. And then the other, then the other branch basically is the normal VGG19, except that we made it fully convolutional at the end. But it's basically an image classification network that has to predict a label for a particular given image. There's one small twist. We actually did not use the original brain data, but we first trained a network to predict neural data, or just straight up on the neural recordings. And then we tried to predict the predictions of this network again, to get rid of neural noise, basically, because a neuron will not answer the same way. It will respond to the image every time you show it. Right, so now how do we test our inductive bias? So we train this network on natural images that are not basically distorted in any way. So it's just clean natural images plus labels and plus predicted neural activity. And we train this VGG19 to predict the label as well. And then at test time, we use different noise distortions and check how well the network is robust against them, or how well it still correctly classifies in these images. And we use it as we use an array of different distortions that are listed here, basically JPEG compression, pixelate, impulse noise, etc., etc. Okay, what you can see here is basically our, let me see that I get it in the right order. It's our best, our median, and our worst network. So for pixelation noise, our co-trained network, so this is the MTL monkey network, does a pretty good job. So you can see on the x-axis the corruption severity, and on the y-axis you see the classification accuracy as you increase the corruption severity. This is the baseline network. This is just a clean network trained on classification, and you can see that the performance is lower, but and it also drops. And you can see that the co-trained MTL monkey, the multitask learning monkey network, does a better job here. So that's still there for impulse noise, and for contrast, it doesn't work that well. We also trained a few control networks, because remember that we only co-trained the first part of the network here. So only this part is constrained by V1 data, and this part can basically do whatever it wants. So we basically wouldn't expect it to be as good as a robustly trained network. In order to test for this, or to account for this, we basically took an oracle, an MTL oracle network, and that's basically this a robustly trained bottom part, or like the bottom part of a robustly trained entire network, or that's the same idea of the multitask learning, but only with predictions from a robustly trained network from this bottom part here. So they basically simulate our robust monkey brain. And you can see that in many cases, the MTL monkey is basically close to these oracle networks, which is a good sign. Okay, so now here's a summary plot accumulating the scores over many different noise distortions. So here's the formula if you're interested in it. But basically what it shows is that when we co-train with monkey data, then our networks become more robust against an array of different noise types, with one exception here. And it's definitely better than some control networks, for instance, where we just shuffle the neural data, basically the images against the neurons to have a control network, because maybe just co-training on some kind of neuroscience data helps, and it's actually not that important what the data contains. But this does not seem to be the case. It needs to be the real data. If you shuffle them, then the performance drops. And what we also checked is that the robustness score correlates with brain likeness. So what you see here is the ability of the network to predict neural data against the robustness of the network. And you can see basically that there is some correlation here. So basically, the better you predict neural data, the better, the more robust the network becomes as well. Okay, so now I want to use my remaining few minutes to show basically the next step in this type of work, and it's this more like some observations and maybe not all the final answers, but it's actually something that we are excited about. And the question is okay, now we established that the network is somehow a bit more robust against these noise distortions, but how are this representation actually different? So this goes more into this explainability question. So what makes this network more robust? And in order, and the way we try to understand it or visualize it is the following, and it's a bit more complicated, but I try to explain this plot here. So imagine that you have images, and this is supposed to be this coordinate axis here. So here we only have 2 coordinates. In reality, we have way more, obviously. And this is the space where the images live. And we have our network, or we have actually different networks. We have a robust model, and we have a model that has not been robustly trained, just different models, and they might be sensitive to different things. And now what we can do is we can try to reconstruct an image from the activities of the network. Obviously, if we have the original image here, so this is a noisy fish, then the best reconstruction will be the original image. So we show the image, we get some activity, and then we try to reconstruct an image by minimizing the distance between the activity of the reconstructed image and the original image. And obviously, the original image will just do the best job and will get 0 reconstruction error. However, what we do then is we put a contrast constraint on these images. That means we don't allow the image to have the full contrast, but only a smaller set. And this is this circus that I show here. And so intuitively, how you can think about it is that the reason why we did this is that we want the network to commit to certain things in the image. So let's say you are the reconstruction algorithm and you have to reconstruct an image, but you're not allowed, you don't have the full contrast budget. So now you need to put contrast in an image where it's important to you. And if you're sensitive to noise, noise is important to you, so you should put the contrast on noise. But if the image content is important to you, you should spend it rather on the image content and not on the noise. And this is what's shown with these ellipses here. So this is a network that is less sensitive against the noise directions. So this is basically an arrow surface here. So you get the same reconstruction by moving along this direction. But if you move in this direction, which would be the content direction, then your reconstruction loss goes up pretty quickly. So you actually care about the content. And what the reconstruction constraint, the contrast constraint does in this case, it will bias the reconstruction towards certain directions than others, because you can get closer to low error if you take this route here and just taking this route here. All right, let's look at a few results. So these are different, so each row is a different norm constraint, and each column is a different model. And just take a look at this norm 15 constraint here, which refers to like maybe this area here, where we should see a difference. So you basically can see that when we reconstruct an image from the baseline network, then we basically, it reconstructs almost everything. So it's a noisy image. So it does reconstruct some of the fish, but it also reconstructs a lot of stuff in the background here. Same with the MTL shuffled, our control network that shouldn't be good. And yeah, you cannot see the fish actually nicely. These are our Oracle models. So the models that we use as a control that cheat a little bit. And you can see that they seem to reconstruct the fish much better. So basically we care more about content than about noise. And this is our Monkey co-train network. It also seems to care a bit more about the fish, but in a different way. It seems to kind of enhance edges a little bit more than the MTL Oracle network and some other controls. Here are a few more examples. So here's a noisy bird. And again, you can see that you basically seem to enhance edges a little bit. In general, the more robust networks seem to care more about the content first and less about what's in the background here. So that basically maybe gives you an idea about how these networks, what they represent differently. However, when we looked at many of these images, we kind of noticed that it might be like it seems to reconstruct things first where we would automatically look at as well. So let's say at more salient parts of the image. And then we simply tried to quantify this, and we took a saliency network, so a network that predicts where humans will look like. So this is a little bit of a confounder because it's actually a monkey v1. So maybe monkeys don't look at the same things as humans. Particularly humans, for instance, like to look at text, and I don't think that monkeys are that interested in text. However, we try to like select images where we have like natural scenes, and we use like a humanly trained saliency network, and then try to use that to find out where humans would look in this image. And then we checked whether our network would put more contrast in the reconstruction inside the salient region than outside the salient region compared to some control network. And this is what you see here. So maybe the mathematical details, I'm happy to explain them, are not that important, but it's basically what this measure measures is does the reconstruction put more contrast in a salient region than in the other region compared to another network. So on the y-axis, you always have the monkey co-train network, and on the x-axis, you have any other network. So for instance, the Oracle network, the baseline network, or some spectral control. And what you can see is that for lower norm constraints, so you should actually see a difference, the actual points move towards the monkey network. That means that the monkey network puts more contrast in actual salient region. And this is an observation. We have not fully understood this, but we find that quite exciting, in particular, since there are also theories of bottom-up saliency in V1. And it's quite interesting that a co-train network seems to, at least for the images that we tested it on, prefer salient regions. That's it. So what I hope to convince you at least, or like motivate to you today, is that mammalian visual systems have a better inductive bias than deep networks, which is one of the reasons that they perform better, they generalize better. That multitask learning might be one avenue to improve the inductive biases of models, and also to understand what the difference is between brains and artificial networks. That co-training on Monkey V1 yields robustness on classification models, that the more brain-like it is, the more robust it becomes, and that co-trained representations seem to be more sensitive to salient image regions. Here are some funding for this work. Before I thank you, I want to thank my group, which is actually a really great bunch of people from all sorts of different places on the world. If you want to join us, we are looking for PhD students and postdocs for probabilistic machine learning in life sciences, the things that I talked about, but also in a broader context, So if you're looking for jobs, please reach out to me and then let's talk. And now, thanks to you, thanks for listening, and I'm happy to answer any questions.